Okay, so did I save something for my starting point? My projects. Is this it? All right, good enough. All right. So, how'd the homework go? Too easy again? Where's the guy that said the homework last time was too easy?
Spent 20 minutes on it, so.
Right here.
Then drop the class. Oh, you're here. You're online.
I'm online.
All right. Was this one was this one too easy again?
I went to the computer science club meeting, so they helped me.
Did you learn from it? Well, so there's your plug for going to the CS club meeting. They'll help you with this stuff. Just make sure you learn from it.
I did. I actually enjoyed it.
Oh, good. So I need to make the next one a little tougher then.
Well, let's not and say we did. How about that?
All right. Well, let's see how hard this one was. Let's start with that. All right. So fill an array with 50 random numbers between 1 and 100. Okay, so we're filling it with 50 numbers, and they're going to be numbers in the range of 1 to 100. Write a function that can display the contents of this array. We've kind of already written that one, but we'll just repurpose that. Then write another function called sort array that takes in a pointer to that array, like we talked about last class. And it doesn't return anything because we're going to be making those changes up in memory, right? We're passing in the address where it can make the changes to the real array. So we don't need to return the changed array because we made the updates inside of its original location. But it should leave the array in a sorted state from smallest to largest. You can only use stuff we've done in class, so hopefully none of you like found the C++ sort function and just boom, sort done. All right, so let's go and look at this. All right, well, I already have some functions here from the last assignment, right? So we have fill array. Oh, I haven't written those yet. We gutted it. Okay. So I guess let's just use that guy. So we're going to say fill array here. And we're going to pass this guy an array of size 50 and we're going to fill it. So let's go ahead and build my array out here first. So right at the beginning of the program, I'll go ahead and seed my random number generator. I could do it at the beginning of my fill array thing, but you just have to do it once. It's not a big deal. So I'll just do it right at the beginning of the program. I'll seed it. So now I have randomness. Let's see. And then we're going to say int, we'll call this guy the array of size 50. All right. Then we're going to go ahead and we're going to call fill array and we're going to pass it the address of the array. Actually, we're not going to pass it the address of the array. The array already holds an address. And we're going to pass it 50, the size of that guy. And I think I kind of showed you something along these lines last time, but I'm going to just create an integer here. We're going to call this guy array size. We'll set that equal to 50. And then we'll just use array size in these two places. That way, if I decide I want to make it a larger or smaller array, I only need to change that one variable. So I'll just change this guy right here and it'll automatically update in these two places. All right. So let's go down to fill array now. This fill array should go through and fill that array up with random numbers between 1 and 100. All right. So down here, we're going to have a loop for int I is equal to 0. I is less than whatever the size that was passed in our example here, that's 50. Now we can use the I++ because we learned about that last time. Remind me, what's the difference between whether the plus plus comes before the integer or after the variable? If I say plus plus I versus I++, what's the difference between those two? Go ahead.
If it comes after, it's not going to update till after it goes once.
Okay, so if it comes after, if I'm using the value right now, so if I say see out, let's just go with size here. If I say see out size, this is going to give me a 50 right now, based on my example. If I say see out size plus plus, this is also going to display a 50. But after this line, it will have become a 51. As opposed to if I say plus size, this will display a 51. And then it will have stayed a 51 after that. So either one, it does increase the value of size by 1. The difference is if I'm doing this in line, will I get the old value or the new value? I get the new value if the plus is beforehand. I get the old value if the plus is afterwards. Okay, but I told you that a good rule of thumb is to always just do your modification on its own line. So now if I say size plus here, I get the same result if I say plus size, because I'm not using the value to the next line. It has changed by the next line, regardless of where I put the plus. Make sense? So this is better programming practice, in my opinion, rather than coming up with cool ninja moves where you embed your pluses inside of a larger expression, where you're now reliant on knowing what value you're going to get based on your location of the plus operator. All right, so we'll go through every bucket of the array. Each time through, we're going to say the array at bucket I, we're going to set this guy equal to something. So remember, if I just do rand, this gives me a value between 0 and the we figured out 2.1 billion, right? Size, the maximum size of a signed integer. I want it to be a number between 1 and 100, right? So if I mod this by 100, I'm going to get a value between 0 and 99. If I then add 1 to that guy, I'll put this in parentheses. I don't think it was actually necessary, but we'll do that. Add 1 to it. Now I have a number between 1 and 100. Everybody's cool with that? So this function right here will fill that array up with random numbers between 0 and, or between 1 and 100. Let's prove that that's the case by implementing, again, our display array. So there's our void display array. We're pretty much going to have the same for loop. Parent I is equal to 0. I is less than whatever size was passed in, I plus. And we'll do cout the array at bucket I. And then let's go ahead and do that little, put a space after it. That way it's more compressed into a, it wraps on the same line. And then we'll kick it down a line here at the end. If standard lib. One thing you can add in now, I'm not sure this necessarily will benefit you tons, but since we've now included standard library up here, you now have this new keyword called endl. So what you can do is instead of the \n, you can say endl like that, and that'll end the line. It does the same thing. One's not better or worse than the other one. Yeah, I don't think so. In fact, the endl is probably a what's called a global macro for \n, would be my actual guess. But save you from having to hit double quote a couple of double quotes and stuff. The reason I didn't show you that before is that it is something that lives inside of standard library. So I didn't want, for something stupid like that, I didn't want to have to talk about importing another library. But since we are now using random number generators and we have the library already, now we can talk about it, I guess. So bottom line is, when we talk about including external libraries like this, you can think of these as kind of like, when you go to Home Depot and they sell those various toolkits, and you have kind of your generalistic toolkit for all household repairs, has the hammer, some wrenches, screwdrivers. That would be like the, the thing that's automatically included without you doing anything special. That's the core programming language that's included. But then you can go to, at Home Depot, they might have some specialized toolkits like a ratchet set or something like that. Certain tools that are made for very specific jobs, that maybe you do once in a blue moon or something like that. Well, you would come home with one of those toolkits for when you need to do that kind of stuff. So including some of these other libraries is kind of like getting one of those specialized toolkits. You know, it has stuff in it for other things that maybe aren't commonly used, but you might need sometimes. In this case, we need to get access to the current time. So we're bringing in the time toolkit. So it's a library of functions related to time. And then we're also bringing in this, the standard library thing that has some extra, almost common tools, but not things that it's going to put into a core C++ program. Anybody know why it doesn't just give us all that stuff by default? Why would you guess that it gives us only the bare minimum number of tools without doing anything special, as opposed to including, for instance, standard lib in a generic program? Yeah, size of your ultimate binary. So if you let's assume that you have every tool under the sun. So we'll take this, you know, to the extreme. You've gone to Home Depot, you've bought every single specialized tool set they have. Okay, and you load them all in the car. The car is going to weigh a lot more than it did without those tools, right? Okay. Even if you don't use the tools, you're still driving around with all those that extra weight. Same thing's true here. Whenever we include something like one of these, effectively what it's doing is it's replacing this line right here with the entire contents of this library. And let's assume we use 0 of those functions. All of a sudden, when we compile our program, the size of that executable file will now be much larger, because we brought all these tools along, even though we didn't use them. Make sense? One interesting thing we have access to, and you sort of have access to it in C++, I guess, but something that is built into some newer languages like Java and C#, is you can be much more specific. You don't have to bring in an entire library. You can say, I only want this object or this function. Okay, so you go to Home Depot, you just buy the one wrench you need, not the entire set of socket wrenches of which you use 1 or 2. So it allows you to be even a little bit more memory efficient or whatever. Okay, so, you know, that's kind of the story with these libraries. But so the reason I didn't talk about Endel before, even though maybe you've seen it in some online examples, is because I didn't want to have to talk about including a library then. But we're using it now, so poof, you have Endel. So I'll put it in there for now and we'll leave it. And it's possible I might write those interchangeably for a little bit as I convert my current mode to you now can use that. But we'll see. But I don't care what you guys do. If you like to \n, leave it. Otherwise, use the Endel. All right, so display array, we have our standard for loop. It's going to go from bucket bucket 0, all the way up to the size -1, incrementing by 1 each time. We'll output whatever we found there, followed by a space, kick it down a line at the very end. So up here, now we should be able to call our display array with the array and array size, and we should get our 50 numbers between 1 and 100 not sorted. All right, so we're good with that. All right, so now the job is to sort it. So we're going to write a function called sort. Did I tell you what to call it, or did I just say sort? Sort array. I probably said sort array instead of sort, because I want to say one of the built-in functions is called sort, and it might be inside of standard lib. So that way you don't get it yelling at you that this function's already written. What are you doing? Blah, blah, blah. So we'll call it sort array. Again, it's going to take an int pointer as a parameter, and we'll take in the size. Why do we have to pass around the size of an integer array? Yeah, so in C++, arrays don't know their length. In newer languages, Java, C#, they do. So if we were writing the same thing in Java, we would not need the size. because we can then ask the array, what's your length? And it would tell us it's 50. But C++, they have something like that, more a newer type of object that operates like this. It's called a vector. If you've seen that in some of your, Google searching or something, but I don't introduce it. I want to stick with the bare essentials of programming and not introduce too much extra stuff. So in C++, if you're using arrays, you got to pass around their size as well. It's just a thing. All right, so for sort array, the mandate here was I wanted you to just kind of figure it out. I wanted you to sit down and think, if I had a whole bunch of note cards that had a number on them and I needed to put them in order, how would I go about doing this in real life just to get it done? Not necessarily looking at an incredibly optimized solution or anything like that, but just a way to get it done. All right. So one approach we might use, I think it's the one I kind of mentioned at the end of class yesterday. We might say, okay, well, I have this pile of note cards that are filled with numbers. There might be some duplicates, but it's 50 random numbers. Maybe what I do is I go through this, and the very first time I find the smallest number, right? I find the very smallest number and I do something with that. All right. Let me actually think about this. What I might want to do actually is find the biggest number. And let me kind of talk about why. So let's start by writing a function called find smallest. All right. Keep things as little as possible. So we're solving little tiny problems at once. That's the skill we're trying to come up with as a programmer, is how do I break problems down into their small little steps? So I want to now write the code that allows me to, given a collection of numbers, what's the smallest one? That's it. So we're going to go ahead, and this guy's going to return an int. We're going to call this find smallest. It's going to take a int array as a parameter as well as its size. So we see a lot of repetition here. Same for loop, right? For int I is equal to 0, I is less than size, I plus plus. All right. But now what I'm doing is I'm looking for whatever the smallest value in there is. So what I'm going to start off with is I'm going to have maybe an integer, and we're going to start this guy off with as the array at bucket 0 is going to be my current winner for smallest. And then I'll start looking at the rest of the collection starting at bucket 1. So I'll remember the very first element of the array. I said, okay, well, right now my best guess is this is the smallest value. Then I'm going to go through the rest of the array trying to find a value that's smaller. So I'll ask the question, if the current value I'm looking at is less than smallest, if I found a new smallest value, I'll replace smallest with the current value I'm looking at. Make sense? So when this loop is done, my variable smallest will hold the smallest value in that array. That's it. I went and looked at every single number, and whenever I had a new smallest value, I replaced that guy as the new smallest value. So when I'm done checking the entire array, my variable here called smallest will hold the smallest value. We're good with that? And then what I'll do at the end is I'll return smallest. So now I have a function here called find smallest. Now, just because it, well, let's leave it at that for right now. I'm going to be making a shift to that. You're going to see why here in a second. All right, so for sort array, what we're first going to do is we're going to go ahead and find the smallest value in the array. All right, so we're going to say int smallest is equal to find smallest the array size. So I'll go ahead and pass my array and the current size into my function called find smallest, which I implemented here, but I prototyped it beforehand, so it doesn't matter what order I implement them in. All right, so I'm going to call find smallest from inside a sort array. So now this guy knows about the smallest number. All right, so now I know that this needs to be the value that will be the very first element in my answer, right? So maybe I go ahead and I say, well, I'm going to have an answer array. Okay, temporary, we're going to create a temporary array of size 50 that we're going to use to build up our answer. And then in the end, we'll copy all that back over. Okay, so again, this is just one approach you can use. We're trying to solve this problem like we solve problems in real life, but doing little tiny steps at a time. So I'm going to create a int array. We'll call this guy answer array, and he will be of size. All right, so I will go ahead and find my current smallest value. Now we know we're going to have to go through every element of that array. To fill my answer array up, I'm going to have to go through and find the 50 smallest values in order, right? So we'll have our same for loop again. For int I is equal to 0, I is less than size, I plus plus. So we're going to do something size number of times. And we'll go ahead and we will get the initial smallest value. Now I know that I can now put that value in answer array at bucket I is equal to smallest. Okay, so I got my big pile. I went through, I found my smallest value, and I went ahead and put it at bucket 0 of my final solution. Okay, but now what do I need to do? I need to remember that I marked that, that was my smallest thing. I'm throwing that out, right? I don't want to find that number again later. Make some sense? All right, so since I don't want to find that number again later, I probably need to have some way of marking it in my original array, letting me know that it was already found, right? That guy, that bucket that I already grabbed as my smallest value should not get found again in the future as a new smallest value. All right, so how might we accomplish that? If I have a collection of cards and I have discovered the smallest number in there, and I've recorded that a copy of that value over here in my potentials in my solution, but I now want to somehow flag this card as not being eligible for being found again. In real life, maybe you kind of fold the corner or something like that, right? Or you know, real life, you lay it to the side, so now you only have 49 values, but we have 50 values. So maybe I'm going to fold the corner, kind of mark that so I don't accidentally look at that one again. Okay, well, we need to find the equivalent way of doing that in this program. So what might you do? Well, one approach we can use that's a common approach, and I'm looking at it in this order, which I'm going to say is not a great way of doing it. We're going to end up finding the largest when we're done here, is what do we replace? So maybe we can replace that smallest value with a very, very big value. So at the very least, it is not the new, won't get captured as the new smallest value. So let's say the value I just found was a 5. If I overwrote that 5 with the largest possible integer I could, 2.1 billion, chances are 2.1 billion will not be the next smallest number, right? Now, remember, I've already copied that 5 over here. So I haven't lost that value. I've copied the 5 here. So now I'm safe to come over here and rewrite the 5 into some giant number, right? So I can set it to 2.1 billion, and we can say, hey, there's a pretty good chance that 2.1 billion will not be the next smallest value out of my 50 numbers, right? But it could be. Why is 2.1 billion a problem? Actually, in this particular case, it wouldn't be a problem. Answer both of those questions. Why might it be a problem, and why isn't it a problem in this case? Go ahead. Only if I'm incrementing. If I'm incrementing it, it could go negative. But let's assume when I did my fill array. Right now I'm filling my array, so it's only filled with values between 1 and 100, right? So guaranteed the largest real value in there is 100. So actually I could mark that 5 as 101 if I wanted to, and marking it as 101 is as good as saying I've now checked this one off the list, right? Because that is guaranteed not to be a value in that collection. But let's assume that all I said here was rand. I filled it up with just the random integers. Why would, so now my array is filled up with values between 0 and 2.1 billion. And let's say that the smallest value I found was a 5. Why would replacing that 5 with the number 2.1 billion be potentially problematic? Good. 2.1 billion is a legal number in my collection of values that array might hold, right? So, I don't want to mark a value as already being used with a value that might be in the collection. Okay, so maybe we might say, well, why don't we maybe mark it as a -1? Flag it as a -1 because I know -1 isn't in the collection. Why might that be a problem? Go ahead. Yeah, -1's my new smallest number. Especially in this case, because my values are 0 to 2.1 billion, right? So -1 is guaranteed to be my next smallest number. That's a bad choice as well. Make sense? So one thing I could do is I could do this backwards, and I could find the largest value each time, marking it off with a -1. We could just say -1 means I'm done using this. And then I will have already found my 50 other numbers before I ever get to that -1 or the next largest. But in this case, since we know that our range of values is 1 to 100, setting it to 101, flagging it as 101, or setting it to 999 or something if we want to have it be more visually, this is checked off or something, that's guaranteed to not be a value that is legal in our collection in this case. All right, so the question is where do we mark that? So when I found the smallest value here, I went through and I just kept track of whatever the smallest value I found was, and then ultimately I returned that number. This was the opportunity when I was going through here for me to remember where I found that number in the collection, in that array, as I'm sifting through my array here, looking for the smallest value. You know, originally I said, oh, I found the smallest value at bucket 0 because I haven't looked at anything else. And then maybe at bucket 4, I found a smaller value. So I say, okay, well, this is my new smallest value, but I found it at position 4. You know, so in the end, you have your actual smallest value, but you also have where you found it, so that you can mark that as already found before you return your answer. So what I could do here is I can keep track of 2 different things. So maybe I keep track of the smallest position as well. So initially I guessed that the smallest number was at bucket 0, so I saved the position at 0. When I find a new smallest value, I would set smallest pause equal to the location where I found that guy. So after this for loop, before I get to return smallest, I have 2 different things I've remembered. I know my smallest value, and I know where I found it in my array. So I could, I'm purposely doing this wrong. So I could say, well, the array at bucket smallest pause is now going to be equal to 999. I'm flagging it as this number is definitely not going to be my next smallest because I've made it a number that's larger than any number that will exist in my collection. Fair enough? 999 is way bigger than 100. All right. So I flagged it as 999 at location smallest pause, which is where smallest was found. All right. Why is what I have written there a problem? Right logic, wrong order. Why? Remind me, what does the return keyword do? Yeah, so the biggest thing the return keyword does is it makes a function immediately end. It also can potentially return a value. In this case, I'm saying kill the function and return this value, which is what I've advertised my function will return, an integer, which means I will never get to this line. Now, the compiler will yell at you and say this line is unreachable because it comes after the return statement. So what I really want is I want this guy to happen before I return. So I've already stored two pieces of information. I have in a variable the smallest value I found, and it's a copy, right? I have a copy of that smallest value. And then I also have a copy of the position of that smallest value. So now what I'm going to do is I'm going to overwrite in my array, was placed in memory, at that position with a 999. So I don't accidentally discover that position as my smallest value again. And I'm still holding on to that in my example I had with my 5, right? And that's the number I'm going to return is the 5. So that's what I did right here. So down here in sort array, I create a new array that I'm going to use as a temporary storage location to fill up with my 50 smallest values I found, right? So I'm going to go through and I'm going to find 50 values. I'm going to call find smallest on my array, my original array, not my copy. So I'm not doing an answer array. I'm passing it the same array in memory over and over again. I say, find the smallest value. It gives me a smallest value, and I know I've now also marked the location of that with a 999. I'm recording that smallest value, and then I'm saying, find me the next smallest value. So it's going to find me the next smallest value and mark its location as 999. I'm going to put that at bucket 1. Find me the next smallest value. Mark the position of that as 999. Put that at bucket 2, so on and so forth. All right. So for sort array, I'm going to go through bucket 0 through 49, filling up my answer array, which is a different array than the original, with the smallest values. All right. So I'll say answer array at bucket I, so it'd be bucket 0, then bucket 1, then bucket 2, then bucket 3. Fill that up with the smallest values. Okay. Now I actually don't even need to store this in a variable if I don't want to. I could just say answer at bucket I. You get the value returned by find smallest with the array and the size. And we happen to know that every single time we call find smallest, it will boil down to the smallest value it found, but it also has the side effect that it's marked off that position in the array with a 999, which will not be the next smallest. We're guaranteed to have 50 numbers in that array that are smaller than 999 initially. Second time through, we're guaranteed to have 49 numbers in that array that are smaller than 9999. Rinse, lather, repeat. So after this for loop is done, we have filled up answer array with 50 values, the smallest values. So after this line, answer array holds the 50 values from smallest to largest. And we can go ahead and prove that by calling display array on answer array and the size of it, proving that we got the right values. We don't have them in the right final location yet, but we have the right values. All right, so let's go back up to main and kind of see where we're at right now. So first thing we do in main is seed the random number generator. We only need to do that once. I set my array size to 50. I build my original array. So I have 50 empty buckets. I fill it with 50 random numbers between 1 and 100. Then I'm calling display array currently. So that should show me my 50 numbers out of order, unless I hit the lottery and randomly generated 50 numbers that are all in numerical order. Extremely unlikely. Then I'm going to go ahead and call sort array, passing it the array and the array size. And remember, at the bottom of sort array currently, I go ahead and display my answer array, my temporary array that I put over here to the side that I filled up with my numbers in order. I'm going to display that. So what I should see now is my original numbers out of order, and then my original numbers in order, but not in the right place yet, because I haven't put them back into the original array in the right order yet. I've just proven that I've got them stored in the correct order in this like secondary little pile over here. Okay, so let's see if we got that. So there's my original out of order, and here's my new one in order. So now all I have to do is spin through my array, copying bucket 0 from here, overwriting bucket 0 up in my original array. Bucket 1, overwriting bucket 1. Bucket 2, overwriting bucket 2. Copying them back over, right? So what I'll do here, so we just proved that we do have the correct values in the correct order. We've just stored them inside of answer array here. Now we need to go and put them back into the original array, overwriting the original array with those values. Now, what values are currently in the original array? If I were to display the original array here, what would display? A whole bunch of 999s, right? 50 of them. So if I run this right now, we will see that we have marked that second array with 999 50 times for the 50 smallest values we found. Make sense? Okay, so hopefully you see the reason I'm doing it in these little tiny steps and then showing you the steps. We're kind of revealing what's under the hood, right? We're seeing how this is progressing. And this is really the approach you should be taking when you're doing your homework right now. Because until you get better at this, where you can just conceptualize a majority of this just in your head, and you don't have to take all these little breathing breaks in between and show you like, okay, does it currently do what I think I made it do? Let's check that. Does it currently give me the output I think it's supposed to give me? Let's check that, so on and so forth. All right. So I really encourage you to follow this process as you're doing your homework now. And then over time, you'll figure out what steps you can skip. And the thing is, you'll always, I mean, CSC200, the software engineering class, which you'll take next fall. So after you take the second programming class, you'll see that that whole class is about planning for larger projects. So as you imagine, as your project gets bigger and bigger and bigger, this is still a tiny project, even though it feels tedious and like lots of functions. None of the functions are doing all that much stuff, right? We've basically written the same for loop 6 times or something. But as our projects get larger and larger, we really need to have a more formal planning process. And that's the point of that software engineering class. The software engineering class really is not a programming class. It's a design class to prepare everything you need to have a team of programmers actually write the software. All right, because there is going to be a limit. I mean, like I said, I've been programming for a couple of minutes, and while I can solve problems of this size pretty easily just in my head, I don't need to take all these little short stops. You do eventually hit problems that are big enough where I need to draw some pictures, right? So you don't go from, oh, I have to plan everything out to I never have to plan again. Just the size of the problems you can conceptualize in your head just grows until you hit some sort of maximum thing where you forget what you were doing. You got to really draw some pictures and give yourself some steps. All right, so now since I'm filled up with a whole bunch of 999s, I know, okay, well, that's meaningless data, right? That's evidence that I did what I thought I was doing, but it's meaningless data. So now I'm free to go ahead and overwrite this 999 with my 27. this 999 with my 40, this 99 with my 12, so on and so forth. So I can just copy everything over to my original place in memory, and then I should have an updated sorted array. So inside sort here, rather than displaying my array here, I'll just write the same loop again. Where int I is equal to 0, I is less than size, I plus plus. And then I'll say the array at bucket I is equal to answer array at bucket I. Just copy those guys back across. Make sense? All right, so now if I go back up to main and I call display array on my original array after I called sort array, we should see that the original values have now been reordered. So there's my original spot in memory that's now reordered from what it was right here. Make some sense? All right, so a couple of questions here. Go down to sort array. So here's my function sort array. What happens to that variable when sort array ends? So we're reinforcing our knowledge of variable scope now. Where was answer array defined? Line 52, right? Inside of the local scope set up for sort array. So this variable right here lives and dies with the scope associated with this guy. So that means as soon as this function ends, when we hit, when we're done with this for loop and this function ends, this memory that was reserved temporarily during the runtime of this function will be given back to the operating system so it can hand out to somebody else, because this function has now ended, and any variables that were defined inside of this function will now get erased. Modern programming languages call this garbage collection. All right, so when the functions end, you have some stuff strewn into memory that's now garbage because we have no way of getting back to it, right? The pointer count for it goes down to 0. And I'm going to talk about that here in a second. So for right now, this guy has a pointer count of 1. And what that means is there is exactly one variable that holds a linked into memory where answer array lives. And that's this variable right here, answer array. If I then said temp array is equal to answer array, what kind of value is stored inside of answer array? Cat, dog, or memory address?
Memory address?
Memory address. All right. So this is just another variable. And actually, this needs to be at int pointer. Sorry. So here's another variable called temp array of type int pointer that holds another copy of that memory address that answer array holds, which means that my pointer count for that memory address just went to a 2. I have 2 different variables that hold pointers to the same memory address. Make sense? What happens with temp array here when this function ends? It also goes away, right? So when this function dies, my pointer count will go down to 0. I no longer have variables that hold the memory address where my 50 values that I had here live. Now, those 50 values are still in memory. They're still up there in memory. I just have no way as a programmer to get to them again, because the variables that I was storing those memory addresses in have now disappeared. So we've abandoned that memory, right? which is why modern languages have garbage collection, which comes through and goes through and finds memory with pointer counts of 0 and says, oh, we're going to give that back to the operating system. We're going to give that back to the operating system, so on and so forth, because that's memory that nobody else can use right now, because nobody has a variable that holds that a pointer to that memory address. Now, what you will find though with like hacker folk is, especially with older languages and older operating systems, they can just pick a starting point in memory and start walking through memory one spot at a time. And this is something we can think about in real life. We talked about memory inside of a computer working like all the houses are one big long street. Nothing keeps you in real life from starting at the beginning of the street and going in and seeing if the door's unlocked at each house down the street to go and steal their stuff, right? You know, nothing keeps you from doing that. You didn't know the address of, you know, the 19th house there. I guess if you knew the base address, you could have calculated that, but you didn't have to know that. You just started walking. You started going house to house until you found a house that had something interesting in it that you wanted. Make sense? So when this function is done, these two variables, answer array and temp array, have disappeared. The variables themselves, which means that we no longer have a variable that we can say, what memory address do you hold that will let us get to the place where our 50 values are? We no longer have that, but those 50 values are still up there. You know, those houses are down the street there and we have our 50 values. And if somebody was able to walk down the street and stumble upon them, they could get to those values again. They just don't have a direct way to Uber to it. Make sense? All right, so realistically, we would say that those 50 values that's wasted memory at this point. So even though the person with the right motivation could get back to them, realistically, from a logical perspective, we're done with that memory. Might as well give it back to the operating system. Modern C++ will do that. So at the end of this function, the memory associated with these guys will disappear. But older C and C++ would have required us to say, delete answer array at the end. And effectively what that says is you are responsible for cleaning up your own messes. You know, if you spill a soda in the kitchen, don't just leave it. You should clean it up before you leave, right? Okay. I'm trying to convince my wife otherwise, but she's not buying it yet. All right, so it's been like 25 years. So that's but in any case, modernly, we kind of sort of have a little robotic, a little robot following us around, cleaning up our messes for us. As a programmer, it allows us to be lazy because we no longer are actually responsible for cleaning up our own messes. Okay, again, I've been trying to get my wife to fulfill that role, and it's turned into just me getting yelled at. Okay, it's a very rude robot is what it ultimately comes down to. Okay, but so as a modern developer, and this is kind of the rationale why I like using C++ as our first language. As a modern programmer, if we jump immediately into our most modern languages, it does so much of this stuff for us. And the thing is, we can appreciate that it's doing it for us, right? All of us would probably love if there was a robot that followed us around and picked up all our messes. That'd be awesome, right? But you appreciate that more because you know at this point in your life what it's like to pick up your own messes, right? You'll do it eventually, right? You'll eventually clean it up, but you know that's this tedious work or whatever, and that something else can do that for me. You know, that's why we have the Roombas, right? That vacuum your house for you instead of having to push around the vacuum cleaner. We can appreciate that because before that, we pushed around the vacuum cleaner ourselves. That kind of stuff. So in old school C and C++, if we got new memory, if we asked for new memory, it was then our responsibility to clean up that mess. So we effectively made a mess right here. We cleaned up that mess right here. Make sense? But modernly, well, we actually have two approaches to it. Modernly, I will tell you that if you define an array this way, it will automatically clean it up. If you define an array let's see, well, I'm just going to show you the generic syntax. If you were to define that array this way, so I'm going to tell you that these two syntaxes effectively will have the same result, the same resulting array. This will create enough new memory to hold this many of these guys. All right. If you want to see a scarier version of this, we can say answer array is equal to the int pointer version of malloc size times size of int. So way friendlier, right? But that's cooler, makes you look geekier, right? It's like when you watch those movies with the hackers in it and they just show the screen of code. If you've paused it on the code, sometimes it's just like some random web page, just HTML or something. It's just meant to look like geeky code. But there are some things that will put real stuff up there that is interesting. But all three of these things effectively do the same thing. And they don't do anything that we haven't already talked about in class. This just looks scary, right? Especially when they put that guy in red. That makes it way worse. Okay. What do you think malloc stands for? It's actually probably the name of a bad guy in a lot of those demon shows. I think, right? But what do you think it stands for here? It makes sense what it stands for once you hear it. Memory allocate. So this is allocating memory, asking the operating system for memory. All right. So I'm saying, computer, allocate some memory for me. How much memory? Well, I need 50 times however big an integer is. So integers are 4 bytes. So I need 200 bytes of memory next to each other. Contiguous memory, right? That's what I need. malloc is going to negotiate with the operating system for me, find my plot of land to hold my 50 integers, hand me back the memory address. I'm going to put that memory address inside that variable. Why did I need this guy here? Because if I didn't put that, by default, this gets returned as what's called a void pointer. Void pointers are generic memory addresses. It'll still be the same memory address. It'll still be the very beginning of the array, the base address of my array. The difference is if it's stored as a void pointer instead of an int pointer, when I go to bucket 1 or bucket 2 or bucket 3, it won't take integer size steps through memory. But the default, it'll take byte size steps through memory. So if I want to get to the 3rd integer, I go to bucket 2, right? But if I have that stored inside of a pointer type, a void pointer rather than an int pointer, when I go to bucket 2, I will have taken 2 byte-sized steps through memory, which will put me smack dab in the middle of the 32 zeros and ones associated with the very first number. Because remember, the first number covers memory address 0 through memory address 3 in my array, right? Because my integers are size 32 bits. So if I'm looking at this array right here, okay, in front of me is a whole series of zeros and ones. The first 32 of those is the value of the very first number in that array. If I take an integer size step through memory, I will hop over all of those zeros and ones, landing at the very beginning of the second set of 32 zeros and ones, ready for my second number, right? But if it's stored as a void pointer instead of an int pointer, then when I say go to bucket 2, it won't know to take 4-byte or 32-bit steps or leaps through memory. It'll just default to 1-byte leaps. So if I'm standing at the beginning of a 4-byte number, or a 32-bit number, same thing, right? 4 bytes, 32 bits, those mean the same thing. And I take a 8-bit or 1 byte step, that's going to just bypass the first 8 zeros and ones, right? Leaving 24 more zeros and ones in front of me before I'm at the end of the first integer. And if I put 24 zeros and ones down, that's a number, right? I'm not getting all the value of the number because I've left some zeros and ones behind me. But if I read that number, if I read an integer from there, I'll get the 24 bits for the rest of this number, plus the first 8 bits of the next number. Probably not the integer we were looking for, because now I'm jumping into the middle of how numbers are stored and just saying, hey, give me the value of the next 32 bits. Probably not the way we want to handle it, right? If I go to bucket 2, I want to get the third actual full integer, the number I stored there. So I need to make sure that I take the proper size steps through memory, where each time I'm stationed right at the beginning of the 32 zeros and ones that represent that number. And in order to do that, we need to make sure that we are operating as an integer pointer, not a void pointer. Void pointers you can think of as like undefined pointers. And our default is taking byte by byte steps, little baby steps through memory. All right. Actually char size steps in C++. Which is why that when you call malloc, when you allocate a memory address, it's allocating an amount of memory that's generic. I told it I want this many of these guys. Size of int in C++ will be 4 bytes. I think we had looked at that one other time. All right, so 50 times 4 is 200. This will go and get me 200 bytes of contiguous memory. It'll come out as a void pointer. I can say, go ahead and label yourself as an int pointer. That way, when I use it, it'll take the appropriate steps through memory so I don't have to do weird bit math. It does become a fun type of thing to sit there and manipulate memory like this and get like half answers to numbers and things like that. But realistically, it breaks our logic of how we're solving problems. We want to make sure that if I want the third integer, I move to the position right at the beginning of that third integer before I try to read it. Okay? Does that make some sense? Now, I know this throws a lot of this under the hood stuff at you. And like I said, in order to be a programmer, you don't necessarily need to directly interact with this stuff all the time. For instance, if you drive a car, you don't need to know that much about fixing a combustion engine or even how the engine works. You just have to know that you turn the key on, you hear some rumbling and stuff, and you hit one of the pedals and it goes, right? And that's good enough to solve problems with a car on a daily basis. The same thing's true as a computer programmer. Okay, and I can say that 99% of the time, not knowing about this stuff will be just fine. But every now and then, when you need to do something kind of at a lower level, or you need to manipulate memory in some way, not understanding how things actually work. You know, I guess we're maybe talking about kind of the Fast and Furious movies, right? We call those the professional car people or something like that. You know, they know how to trick out cars in some ways. So they had to have an understanding of what was under the hood in order to put their nitrous boosters or whatever they're doing to the cars in there. All right. So as computer scientists, we want to be able to leverage this knowledge when we have to. The rest of the time, we'll just drive the car to the grocery store and move on with life. Make sense? All right. But that's what differentiates us from somebody who just went and did a coding boot camp or something like that. Because coding boot camp is going to teach you how to use arrays. It'll teach you how to drive the car, which is fine for a lot of the time, but not all the time. And that's not what's going to get you hired to solve those more difficult problems that do require you to understand what's under the hood. Make some sense? All right. So having said that, I mean, we'll talk about it when we get to the final. There's a pretty good chance that I would never actually test you over that. Because really what I'm interested in this course is your ability to write applied programs. right? So I want to see how you problem solve, because that's really the most important thing that's going to evolve over this, certainly your first year, your first 2 coding classes, but throughout your 4 years here is your programming skills going to continue to evolve. And that's what I'm really looking for, especially in these early classes. Not so much of your deep knowledge of what's happening under the hood, but it's important that we introduce this stuff now, because future classes are going to go into a lot more depth with this. I think I mentioned the 325 class most of you are taking next semester, computer organization. That class talks about the nuts and bolts. It talks about the processors and the registers and how things are actually stored as 32 bits or 16 bits or 8 bits and all those things. And you're going to be operating at this level the entire semester, right? So now that you've been introduced to it, now you kind of have a framework for where this stuff fits. Make some sense? All right. So if this is freaking you out right now, that's not that big of a deal. Don't worry too much about that. The memory stuff, as I mentioned when we first started talking about pointers, it's intimidating because memory is scary, apparently. All right. But eventually you'll realize that computer memory is significantly simpler than real life. In almost every single case, computers are easier than real life. All of us just have a whole lot more experience with real life than we have with computers. So it doesn't feel more difficult. All right. But in any case, back to my the lesson here with variable scope is when we create a mess, it is either our direct responsibility to clean it up, or at the very least, we want to appreciate that whatever tool we're currently using is following us up and clearing that memory that we're no longer using, we no longer have access to. And that's what that pointer count is. At one point in time here, we had 2 different variables. Let's get rid of this guy. We had 2 different variables that pointed to the same memory address that was generated here. When this function dies, both of these variables were local variables, so their scope was local to this function. That pointer count will drop to 0, which means that we have this one little place in memory. Really, it's 50 places in memory. We have that base address that nobody knows how to get to. No roads go there anymore. So since the pointer count is now 0, meaning nothing points there, we can then clear that, give it back to the operating system. And modernly, that's automatically done for us. Now, having said that, on this line right here, what's the pointer count of the array? So the array was defined right here, right? So this guy had a pointer count of 1 after it was defined. So as we go through here, we're in sort array. Does this guy hold the same memory address as the guy up above? That's what was passed in, right? When I called sort array here, I passed it the value of the array right here, which is a memory address. So I passed in a memory address here. That memory address was passed into this variable, which happens to be named the same, but that is a different the array, right? It's a different variable. But how many variables now point to that same memory address? 2. So the array pointer count is now equal to 2. Should have set it to 1 up here, did I? Yep, so after this line, it's 1. We get down to this line. I now have a second variable that points to the same place. So now that memory address's pointer count is now 2. When this function ends, this variable goes away, right? Its scope is local to this function. So when sort array finishes, any variable defined as part of sort array disappears as well, which will mean the pointer counter goes back down to. So after I called that function, it had gone up to 2. When that function ended, it bounced back to 1. Because it's still greater than 0, we do not garbage collect that because there is still a way to get to that memory address. My scope here in main, where I have this variable right here, that still points to that memory location. Inside sort, we had a second variable that pointed to that memory location. Okay, what is, isn't this called, what's that? Doesn't have a name, this dance? Is that dabbing? I think, oh, did I say it right? Dabbing or dapping? Dab. See, I'm cool, I'm hip. That is a funny thing that happens over the years. When I first started teaching when I was 21. And I got my PhD very young. And so I was teaching grad classes. So I had many students that were older than me. Not anymore. So you start losing touch over the decades, and you no longer have the cool lingo, right? You know, back in my day, it was, you know, leet speak stuff, and now there's all these weird, like my nephew the other day said, like he said like, meet us at this restaurant at a certain time. He goes, bet. It's like nonsensical. I get the context. In context, I get what it meant, right? It's like okay or cool, right? Where are they coming up with this stuff? Yeah. Well, probably the funniest misstep I made, this had to be, I don't know, 8 years ago, something like that. And I was not aware of the phrase Netflix and chill.
We know where this is going.
So I a lot of times I spend my weekends, I'm writing code and I'm just watching Netflix and chill. So they all start laughing. I'm wondering why. So I was educated then. See, we learn from each other, right? So in any case, with my move, with dabbing, we have one variable pointing to that memory address. We have another variable pointing to that memory address. When the sort function ends, this guy dies off, but we still have that original thing pointing up in memory. So we have not lost access to that bucket of memory anymore. Okay. So it won't get cleaned up yet, won't get automatically garbage collected or anything like that, because we still have a way of getting there. And that idea of having variables that we can still get to places of memory is a super important thing in computer programming. The entire third class, the data structures course, where we rate these things called linear linked and nonlinear linked data structures, is built around that idea of we have things strewn around memory that are linked to each other, and we have to not lose track of it. If I'm swapping places in one of these things with these two variables, and all of a sudden I stop pointing to that guy and I'm up here, and all of a sudden I go back to find him, I've now lost him. He's floating out in the nether somewhere. Make sense? So we'll draw lots of pictures then and that kind of stuff. Okay, so yeah, I just want to leave this in a good working state to give you the code. Inside a sort array. That's good. So we're still doing it. Where's my 51? Oh, there's my temp array. I don't use that guy. Oh, then there's the delete thing. All right. So I'll give you this code as a starting point. I will put up a new homework assignment for over the weekend. It'll be something along the lines of this one. Continually to practice with with arrays and random numbers and doing something with them and dealing with pointers, that kind of stuff. Okay. But I'll make sure it's much more difficult than this one, since this one was too easy.
It was, for me, it was just kind of tricky.
I think for most people it was kind of tricky. But I'm gonna pretend like everybody found it trivial. All right.
I was gonna try using my the countdowns. The countdown was the basis.
So like, I want this here.
Yeah, fine. Next time we'll talk about an actual, one of our actual algorithms called insertion sort. Code. Yeah, actually, what's funny is insertion sort looks like it should be called bubble sort when you see the algorithm for it, because you pick values and they bubble towards the top, but it's actually called insertion sort. There's also some other, there's a shell sort, and there's a zillion algorithms. They all suck. Okay. When we look at merge sort here, maybe next week, man, you guys are going to hate me. Man, merge sort is so easy to explain and is just an absolute nightmare. It's every student's, you talk to seniors today, ask them about merge sort. Oh, but you're going to write it so many times in my classes that it's such an important sort, and you learn so much from doing it. But we'll learn about recursion when functions call themselves, and merge sort calls itself twice inside the, oh man, your brain goes into knots. It's so good.
Are we good online, Professor?
Yep, you're good. Let me
All right, have a good one.
stop the recording.